Multivariable Calculus, Section 12.5, Optimization. So let's begin by reviewing extrema for a single variable function, f of x. Here's a typical graph, and if we have some nice round places, we can have a global max, we can have a global min, and there's a local max where there's a cusp or a corner there. Now some books call these absolute and relative, but this book is using global and local. Notice that at the nice round min and max we have a zero derivative, and at the cusp we have an undefined derivative. Extrema for a function of two variables. Here we have an example of an absolute maximum, an absolute minimum, a local minimum, a local maximum, and then there's another local maximum back there. Now in the middle, that point right there, you'll notice that if you go right to left, it looks like a minimum. But if you go backwards and forwards, it looks like a maximum. Those kind of points are similar to inflection points in single variable calculus. They're called saddle points. Now here's an example of a nice round maximum on a surface. And you'll recall that the tangent plane was determined by the tangent to the x curve and the y curve. And extrema then, this type of extrema can occur whenever the tangent plane is horizontal. And if the tangent plane is horizontal, then the slopes of these two lines have to be zero. And the slopes of these two lines are the partial derivatives of z with respect to x and y. So the tangent plane is horizontal whenever the partial derivatives fx and fy are both zero. Here's another example of a local max, a global max, and a saddle point. Number 2, find all points where the tangent plane is horizontal given z equals 4 minus x squared minus y squared. So we need both zx and zy to be 0. Zx is 0 minus 2x minus 0 because the only term with an x in it is that middle term, and so this will occur only if x is 0. Zy is 0 minus 0 minus 2y because now the only term with a y in it is the last term, and this can only occur when y is 0. So now we have the x and y coordinates. We need the z coordinate at 0, 0, which is 4 minus 0 squared minus 0 squared equals 4. The only point where the tangent plane is horizontal is at 0, 0, 4. Number 8, find all points where the tangent plane is horizontal given z equals x to the fourth plus y cubed minus 3y. So again, we want both partial derivatives to be 0. Zx is going to be 4x cubed, which again means x has to be 0. Zy is 0 plus 3y squared minus 3, and if you solve that, if you set that equal to 0 and solve for y, you get plus or minus 1. So we have two solutions, and now we have to find out the z value. So we plug into the original equation, 0 and 1, and we get z equal negative 2, which gives us the point 0, 1, negative 2. And then we plug in 0 and negative 1 into the original equation, and that gives us 2 for z. So our second point is 0, negative 1, 2. So 0, 1, negative 2 and 0, 1, positive 2 are the only points on this surface where the tangent plane is horizontal. Number 10, find all points where the tangent plane is horizontal given z equals this function in x and y. Well, now recall from single variable calculus that the derivative of 1 over f of x is the opposite of f prime of x divided by f of x squared. So we use a similar formula to compute our partial derivatives. For zx, we have the denominator squared, and then the derivative of the denominator with respect to x, using pretending that y is a constant, gives us negative 2 plus 2x, so we take the opposite of that and get positive 2 minus 2x. And this is going to be 0 when x is 1. Similarly, zy is the denominator squared on the bottom, and then the derivative with respect to y, treating x as a constant, would be 2 plus 2y, so we take the opposite of that for the numerator, negative 2 minus 2y, and this will be 0 when y is negative 1. And so pretty straightforward. We get our point, z of 1 comma negative 1 is evaluated with x being replaced by 1 and y being replaced with a negative 1, and that comes out to negative 1. Therefore, the only point where the tangent plane is horizontal is going to be 1, negative 1, negative 1. The tangent plane is horizontal at 1, negative 1, negative 1. Number 12. How many tangent planes are horizontal to the surface given by this expression? Okay, so here we go with the partial derivatives again. Here we have to use the product rule, using 2xy as the first function and the e to that quantity as a second function. And so the derivative with respect to x of 2xy is 2y, and then we leave the e quantity alone, and then we add 2xy times the derivative of the e quantity, which is the e quantity times its derivative with respect to x. So it's negative 1/8 times the derivative of 4x squared, which is 8x. Simplifying that, we factor out all that we can, and we get 1 minus x squared in the parentheses. Now this gives us two solutions though. Y could be 0, or x could be plus or minus 1. Now the partial derivative with respect to y is very similar. The only difference really is that the derivative of 2xy is 2x, and the derivative of the exponent of the second part is negative 1/8 times 2y instead of negative 1/8 times 8x. And again, we can factor out what we can, and we get two solutions again. Either x is 0 or y is plus or minus 2. So now we have a cornucopia of points. Here are all the combinations of x's and y's. And then what we're going to do is we're going to plug those into the original equation for z to figure out what the corresponding z values are. And there they are. Now you'll notice that these two are the same. So we're at the same z level. So those points have the same tangent plane connected to them. And these two z values are the same. So again, those 2 points will give the same plane. And then the last one is a third plane. So there are only 3 tangent planes horizontal to this surface. It's just that 2 of the planes touch the surface at 2 points. 22. The following function opens upward or downward. Find and identify its global extreme point. And here's the function. So again, we start with our partial derivatives with respect to x. And this one we are using the product rule, so it's the derivative of 1 plus x squared, which is 2x, times the exponential term, and then plus the 1 plus x squared times the derivative of the exponential term, which is the exponential term, times the derivative of the exponent with respect to x, which is negative 2x. We can factor that, and the 1's cancel, and so pretty obviously the only solution is x equals 0. And here's the derivative with respect to y, and notice that this time the derivative of 1 plus x squared is 0. And the derivative of the exponent in that second term is negative 2y. So simplifying that a little bit, or just cleaning it up a bit, we get a solution of y equals 0. And the problem told us there would only be one extreme point. Now we plug that back in to get the z value, and we get 1 for the z value. Now the question is that a min or a max? Is 0, 0, 0, 0, 1 a minimum or a maximum? So all we have to do is check one other point. So I just chose 1, 1, plugged that in, and got 2 over e squared for z. Now that's less than 1, and therefore our 0, 0, 1 must be the global maximum. Number 28. Find the global extrema of f of xy equal xy squared on this domain. Well, here's the domain. It's a disk of radius root 3 centered at the origin. And so the global extrema could happen somewhere in the middle, which we would find out by examining the partial derivatives, or it could happen on the edge of the disk. because it stops there. So that's kind of like an end point in single variable calculus. Instead, we have an end circle. So the partial derivative with respect to x is y squared, which yields y equals 0. And the partial derivative with respect to y is 2xy, which yields x or y equal to 0. And so basically x can be anything, but y has to be 0. So if we plug in any x value for x, but we plug in 0 for y, we're still going to get a z value of 0. So let's take a look at the edge. The edge of that region is x squared plus y squared equals 3, or y squared equals 3 minus x squared. And we're going to plug that back into the original, and that'll give us g of x, a single variable function in x, that we can find the extrema of. So we've got x times 3 minus x squared, which simplifies to 3x minus x cubed, and it will have its extreme values when g prime of x equals 0. So we've changed this into an easier problem. So we take the derivative of that expression and solve for x and get plus or minus 1, which means that if there's a min or max on the circle, it would have to occur when x is plus or minus 1. Now we plug that back into our value for y, and that means that y would have to be plus or minus root 2. So then we plug those values into the original function to find z. And if x is positive, it doesn't really matter if y is positive or negative. So we get 2 for positive 1 for x. And for negative 1 for x, we get negative 2 for z. So pretty obviously that's the global max, because 2 is bigger than 0, what we found out earlier from the partial derivatives. We got 0. And the negative 2 is the global min. Now, what's happening at 0? Well, that's probably a saddle point, but they didn't ask, so we won't tell. Number 34. Find the point in the first octant on the surface defined by x to the 4th, y to the 8th, z squared equal 8 that is closest to the origin. So we don't really know what that surface looks like, so we'll just draw a generic surface. And we want to minimize the distance, the blue distance, from the origin to a point on the surface. So our distance, using the distance formula, would be the square root of x squared plus y squared plus z squared. And that's inconvenient in an optimization problem to have that big square root. So instead, we'll find the minimum square of the distance, and that will give us the same point. So the first thing we want to do is eliminate one of the variables if possible. So I solved for z squared and then substituted that into our function d that we want to minimize. So now we have this function. Now in order to minimize it, then we need to set the two partial derivatives with respect to x and y equal to 0. So here's a partial derivative with respect to x. And if we set that equal to 0, we can solve it for x and y. And then when we do this again for the partial derivative with y, we'll have another expression in x and y, which we will then be able to use together with this one to solve for x and y. So here's the partial derivative with respect to y. Set it equal to 0, and we get x to the 4th, y to the 10th equals 32. So we're going to put those together. If we double the first expression, then it should equal the second one. And now we can solve for x and y in terms of each other. So now I'm going to substitute 2x squared for y squared in that expression with the blue box. And so we get 2x squared to the 4th for y to the 8th. And we can solve that for x. X turns out to be 1. And that means over here then that if x is 1, y squared is 2, and y then is the square root of 2. Remember, we're only in the first octant, so we're using the positive square root. Now we can substitute into this expression to solve for z squared. The z squared is a half, and so z is 1 over root 2. The point on this surface closest to the origin is 1 comma root 2 comma 1 over root 2. Number 38. Find the dimensions of an open top box with the volume 4,000 cubic centimeters that minimizes the total surface area of the box. So here's a picture of the box. And we know that x, y, z is 4,000. And so z, since we want to eliminate one of the variables if possible, is 4,000 x to the negative 1, y to the negative 1. And we want to minimize the surface area, which is the bottom xy, plus the sides, 2 of which are xz and 2 of which are yz. So I'm substituting for z, and now I have an expression for the surface area in only x and y. And I can simplify that a little bit by multiplying x times x to the negative 1. And now we have our partial derivatives, first in terms of x, and then in terms of y. And you're probably getting pretty good at computing those by now. And so we set them equal to 0, and solving the first one, we can then substitute what we got for the first one in for y in the second one. Simplify, solve for x, and we get x equals 20. Now we can work backwards, and we find out that y is also 20. And finally go back up to the top and solve for z, and z ends up being 10. The dimensions that minimize the surface area of the box is a base of 20 centimeters by 20 centimeters and a height of 10 centimeters. Number 40. A closed box has a volume of 48 cubic feet. Material for the top and bottom costs $3 per square foot, and material for the sides costs $4 per square foot. Find the dimensions that minimize the cost of the box. So this is similar, but it's a little bit different. So there's a picture of our closed box. XYZ is 48. We can solve for z again in terms of x and y. And our cost is going to be 2 tops and bottoms at $3, both x, y, and then 2 sides that are xz and 2 sides that are yz, each at $4. So we're multiplying by the number of sides and by the dollar cost. Substitute for z so that we only have 2 variables and simplify. And then take the partial derivatives, one with respect to x, and it will only be 0 if y is 64 over x squared. And then the partial derivative with respect to y, we can go ahead and substitute 64 over x squared for y, and simplifying that and solving it, which I didn't show the work, but I'm sure you can do that, you get x equal 4. So working backwards, y will also be 4, 64 divided by 4 squared, and then up at the top, if we plug in 4's for x and y, we get z equal 3. The dimensions that minimize the cost of the box is a base of 4 feet by 4 feet and a height of 3 feet. Don't forget your units in your final answer. So I will leave you with something that would be inappropriate for you to do. You do not want to paint gang signs anywhere in the school. Have fun with the problems.